So welcome to this Python session. So as Mike was introducing, for good questions, we have this book. For a bad question, I got this, okay? Okie dokie. So I'm Dr. Michael Klemm, and I'm kind of the inventor of this Python offloading infrastructure. And I want to go through with you through what it is and what you can do with it. Okay, why Python? Well, you know, Python is a cool language. It's the second coolest language I know. The coolest is Fortran, of course, just to insult a couple of people here. But you know, the HPC community has gained a lot of interest in Python. So there's Jupyter, formerly known as IPython, which is a quite convenient way of, you know, interacting with a Python interpreter. There's something like the atomic simulation environment, which is really a domain-specific package to simulate atomistic effects. So you can create atoms, and then the package basically creates all the matrices that you need that you can feed into your solvers. There's of course NumPy and SciPy, there's pandas, and you know, if I would be talking about HPC type of packages in Python, I would be here forever. So I don't want to annoy you with that, okay? And then there is the Xeon Phi Coprocessor, which is also interesting, right? And one thing how you can speed up your Python is, and there was a presentation yesterday, you can use the Intel distribution for Python, right? So Intel has recognized that there is a certain demand for high-performance Python. And so what we did is we basically packed up a Python interpreter that is compiled with the Intel compiler, plus NumPy, plus SciPy that links against MKL for maximum performance, and we shipped that as a convenient installer for Windows and Linux, okay? And it also supports, I believe, Python 2.7 and 3.5. So it's, you know, the most common dialects, basically. Okay, and what you get out of that is basically something like a 3 times speed up over what standard Python offers you. And soon we will also have support for macOS, of course. So here's a graph, what you can expect. And I did that myself, basically, looking into Python performance quite a bit. And so what you can see is that, you know, if you take a standard out-of-the-box Python distribution, I'm not saying that it's bad, right? It's just not the optimal performance that you can get. So for instance, on Red Hat-based systems, what you get is a NumPy that is linked against Atlas. Atlas is a very good numerical library, but the problem is they set it up on some build machine at the Red Hat data center. And so Atlas does, you know, auto-tuning towards the system you compile it for. So what you get is not the ideal performance for your local system, but for the build machine at Red Hat, basically, right? And so MKL basically does that for you and adapts automatically to your system, right? Because that's what MKL is supposed to do. And then, of course, we add a lot of multi-threading so that you can actually leverage the cores in your machines and get ideal performance out of it, okay? Now, if that is not enough, and this is now kind of the bridge to what I initially wanted to talk about, is you can use something like the Xeon Phi Coprocessor to gain additional performance out of your code. So this is the agenda of the rest of the session. So a very brief introduction into the Intel Xeon Phi Coprocessor. You can raise your hands if you already know that, and I will skip through those slides. I don't want to annoy you too much. Then I will tell you how you actually can find offload candidates. And the other thing, then the major part of the section will be the Python offload module and how it works. Okay? So very quick introduction into the Xeon Phi Coprocessor.
Can I ask, is the Intel distribution for Python, is that free?
Yes.
It's in technical preview right now. So.
Okay, so here's the Xeon Phi Coprocessor as a card. There's the typical die shot. I'm sorry, Bill Macro was showing this nice wafer. I don't have a KNC wafer with me, so you bear with me. You have to look at the slides. So this is how it looks like. Okay, so we have slices of cores with a wide vector unit. We have this interprocessor network which connects all the processors on the device. And then we have the GDDR, so the graphics RAM, hooked up to this processor and the PCI Express interface, right? And so you all know that, you know, we have them from 57 cores to 61 cores. And it delivers quite a good memory bandwidth compared to a Xeon system. Now, going deeper into how the core looks like, so we have those two pipelines. One is the scalar unit, one is the vector unit. Obviously, the vector unit executes all the nice 512-bit wide vector unit instructions, and the scalar unit basically takes on all the rest. Okay, it's a bit simplified picture because there are a couple of things in between, but let's keep it that way. Okay, the vector unit, as I said, is 512 bits, so that's a reasonably wide vector. We have 32 of them, so that's a lot of data you can crunch with one single instruction. So it's either 8 times double precision or 16 times single precision floating point. In theory, running at peak performance, the system can use one instruction per cycle, right, in fully pipelined mode. And you can feed, while the vector unit is crunching numbers, you can feed the second pipeline with a scalar instruction, at least in theory, right? It depends on the code mix, but that's what it's supposed to be. Okay, and it's of course a 64-bit unit, and we have the regular coherency protocol between the L1 and L2 cache, so that you don't get any coherency and memory subsystem surprises from a programmer's perspective. Okay? Okay, now how to find offload candidates. Okay, so what's an offload candidate? It's probably the first question you ask yourself. And by the way, please interrupt me. I'm happy to take questions in between because it's more and more interactive and more fun. Okay, so an offload candidate is some code region that seems to be good enough or amenable for offloading. Okay, that's kind of a recursive definition, I know that. But basically, it needs to be compute intensive, right? You don't want to offload something that basically doesn't do any number crunching, because then the coprocessor would sit there idle and look at the code like, yeah, and so what next, right? It needs to be highly parallel. 61 codes, 4 hardware threads each. So you need to have round about 250 threads, right, to saturate the system. And then what's helpful, though, is that the compute scales faster than the data transfer needed to saturate that compute. Okay, typical example is something like a matrix multiply, where the complexity is O of n3, and the data transfer that you need is n squared. Right? And if you go bigger and bigger on the matrix sizes, the compute goes up much higher than the data transfer that you need. So these are good candidates, right? If you don't,
Just a short question.
Oh.
So, how then you define compute intense code regions? Because I thought that exactly third point is definition for the first point.
Yes. Yeah. Okay. Fine. But there are also. Okay. Yes, you're probably right that it's duplication of the first point.
No, I just wanted to understand how else you can define compute intense.
Well, the third point you can actually the third point, if you can keep the data local on the device, you can even have an algorithm that is only n squared, right? But then you need to stay on the target device so that you can keep up, with the computation and actually get the factor that you have in the first place back by doing multiple runs over the same data, right?
Are you going to call out points here where the strategy is going to need to be different on the current Phi and the future one, which is self-hosted?
Basically, compute scaling stronger than data transfer is completely gone, because you don't need a data transfer anymore, at least if you use it in the self-hosted version of K now. Because you are on the processor already, the data is there, and so you can just run.
The issue would be if you had something where you needed DDR because you couldn't fit in the package.
Right.
And I don't know if the caching works very well for that or not.
I don't know either yet. We'll figure that out hopefully soon. Okay, and then how to find that. Okay, so first of all, create a benchmark and run it, right? Find the hotspots in the application and determine input and output data. Okay, and then in the second or last part, you determine how much data you actually need to transfer and what data to transfer. Okay?
I have a question about that.
Yeah.
So I know yesterday y'all were talking about how VTune now supports Python for profiling, but is there any other really good way of finding hotspots in Python code?
Well, there are, let's put it this way. It's exactly the answer of that slide, basically.
Okay.
So there are three ways, right? The hot way, you actually stare at the code really long and hard to find out what it is doing, okay? That's especially problematic if you have 5 million lines of code, okay? So it's not very advisable. The easier way, and that's the answer to your question, yes, there are profiling tools for Python, but to use a technical term here, they suck, right? Because I went through that exercise in my own life. It gave me a lot of gray hairs. Basically what it means is you need to augment your code to make a sensible analysis for big codes, right? You know, cprofile is a perfectly fine tool for small programs. If you throw 200,000 lines of code at cprofile, good luck with that, okay? And then the right way, of course, is to use a profiling tool, right? And of course, VTune is the best. I'm probably slightly biased towards the tool. Okay, so this is now the methodology you run through. Okay, basically, as a starting point, you start with a benchmark, you do a hotspot analysis, cprofile, ideally VTune. You do a call tree analysis. The call tree analysis is important because you want to find subtrees in your call graph so that you can potentially do the data transfer at the top spot in your call graph and then offload the whole call tree in one go. That's kind of the idea, right? And that's why you need that. Then you do a loop analysis. So you want to know, are my loops parallel? Are they parallel enough? So can I actually feed 244 threads? And then you add offloading, right? And then you start optimizing the data transfers. And when you're happy with the data transfers, you start optimizing the compute kernels. Why data transfer first? This qualifies, by the way, for a book.
Because if you're still talking about the thing that's across the far end of the PCIe, it's just pathetically slow.
Exactly. So the answer is, and you're right, PCI is really darn slow.
My most compute-intensive kernel discovered that it would take longer to transfer than the computer on the host.
Exactly. So with optimizing the data transfers, you easily gain factors, whereas with optimizing the compute kernels, you probably get lower factors or even only percentages. Okay. And then, you know, and I'm a performance tuner, so this whole step, optimize the compute kernels itself, is another cycle that usually when I go out to a customer takes me 3 days to explain how to do it properly. Okay, so you know it's a bit it's an interesting topic. Okay, so just a quick categorization of what profiling tools can do. So there are the ones that are event-based. So for instance, cprofile basically somehow instruments the Python interpreter, and anytime an event kicks in, it is kind of intercepting the event, recording it, and then at the end it gives you some information. Okay? Then there are instrumentation-based approaches. So basically either you do it or the tool does it. Basically you inject code into the program to monitor it. One example is the gprof profiler of GCC, where you need to compile your program to have the instrumentation in it. And then there is statistical profiling. That's what VTune does. So basically, we don't look at the code too much. We just tell somebody to intercept it from time to time, like a timer. And then we get statistical information after 10 milliseconds or whatsoever the timeout is. Then we know where the program is. And if we get enough of those samples, then we can draw conclusions about the statistical distribution of those events over the program. Okay? And this is exactly what VTune does. Okay? So VTune, that's our own tool that we sell. And so you know it gives you some nice properties that you don't get from text-based programs. So it gives you nice color coding, it gives you timelines, so you can easily navigate post-mortem through the performance data and then draw conclusions about the execution of the program, right? You don't have to sit with the program to do performance analysis. Okay, let me skip that. It's just, it's really, you can, through the color code, you can find easily where the problems are. You can drill down to the source code line that is causing a particular issue. 1 second. And then you can look at the timeline to see how the programs and how the threads of your program evolves over time. Yes, there's a question.
I was guessing, I never remember. Does VTune need the source code or
Not
executable debug information?
Not necessarily source code. Well, if you want to dig down to the source code, you better have it, right? But ideally, you would have a binary with debugging symbols. If you don't have the debugging symbols, it still works perfectly, or you can see assembly code without function names, right? So, but it makes things a little harder and a little more nerdier. I'm coming to that in a minute. Okay, so. Yes, that also works in the latest VTunes. We have a memory analysis right now, and you can even identify those objects that are causing the traffic. It's really, really convenient now. Okay, so here, that's now VTune for Python. It's, as Mike was saying, it's available as a technology preview, so you can register. Please ask Mike about the details. So basically what you can now do is, when you configure VTune to monitor a Python program, it can tell you the Python hotspots. Okay, so here, let's say I did that, and then what I can see here is that there is a certain hotspot called intersect spheres. So that's a Python ray tracing application, and it basically tells me then, again, what Python code fraction caused the performance that I'm seeing on the system. So you can actually drill down through the Python code and find out what is causing your performance issue or where the performance is lost. Okay.
We do all of that with a Linux system with this free.
And Windows, Linux and Windows.
Yeah, there is no Windows that are computer centered, so.
Yes.
That's
Well,
why I always ask about Linux.
yes, Linux and Windows always. Linux always works. Okay, so let me use an example here called GPaw. GPaw is a quantum chemistry application or quantum physics application. It has a couple of users over the world. So the idea here is that the high-level algorithms are implemented in Python, so all the solvers, and then it calls into number crunching kernels written in C and Fortran or some libraries. And it also uses MPI for massive parallelism. Okay? So if you run that, this is actually the VTune profile that I generated a couple of weeks ago. So you see that there is a function called gem. So it seems to be dgem bound. That's the Python hotspot. And so the question is that an offload candidate? Right? And it's called a kind of a stupid question. Yes, dgem is always an offload candidate, right? Because it actually satisfies my requirement that I put up earlier. Okay, so I can also dig into that, and what I can see then is, okay, here again, that's my hotspot. And then over there, that's my call stacks. So I exactly know where dgem was called from the Python code. Okay? Why is this important? And let me give you a short intermezzo. Okay? So I ran that with PyCallGraph, GPaw. It's a 200,000 line code. It gave me a raw PNG file about 800 megabytes. That one. I had to use GIMP to scale it down because PowerPoint was really blowing up on that data size. Okay, let me just grab some arbitrary part of it. Okay, and then you get this. Let me zoom in further. You get this. This call graph is virtually unusable. You create it, you look at it, and it's completely useless to look at it. Okay, you can't infer anything out of it. So what I did is I spent a week, implementing or re-implementing parts of GPaw or augmenting them with special interfaces so that I can actually drill down the call graph to get to the point that I was interested in. right? Here, you can just navigate within an hour, okay, to find out where DGEM is called. Okay, so now the Python offload module. Okay, so as I said, I'm the culprit behind PyMike. So I had 4 Ks in mind. Basically, I wanted to be simple as possible. I wanted to be slim API, so I don't want to have bloatware that I have to add to my code. I want a slim, concise interface that I can use easily. I want fast code, right? Because if it takes ages to do an offload, the more you need to compensate in terms of performance on the target device. So it needs to be pretty darn fast to work. And since I'm a nerd, and I'm one of those stubborn German programmers, I want full control of everything, right? Performance is so important. I don't want to leave it to the system. I want to exercise full control over the system to control what is going on the system level. For those of you that are interested in some more trivial information, so it's BSD licensed, it's fully open source. I will come to that on my last slide. And if you believe that lines of code is a good metric, so it's about 3,800 lines of C++ code, plus around about 1,000 lines of Python code to wrap around that C++ code. So it's really slim in terms of what it is. Underneath, we use libxstream. That's an offload engine that a friend of mine in my team has been implementing. And we use Intel Leo. That's the language extensions for offloading to interface with the target device. Okay, so that's kind of the infrastructure. Yes, please.
Fortran is your favorite language. Why don't you write this in C and C++?
I was joking about Fortran. Well, the thing is, this guy here is implemented in C++, and I'm just pulling it in, right? Okay, so if you build it up, so at the lowest level, we have this offload infrastructure that basically talks to the target device. Then we have a small wrapper around that to make it an offload engine. So basically, this is now plug and play. You could implement something different. Like for instance, in the future, we might have something like offload over Fabric for Knight's Landing. Then on top of that, there is a low-level data management interface that I'm using internally, to have something like a memcopy-like interface to the target device. And then on top of that, there's a nice high-level Python layer that gives you, a nice programming interface to the offloading. And finally, there's a small library that we ship with in PyMike that implements some device kernels. And I'll come to that in a minute. Okay, so let me give you an example on how to offload a DGEM. We already sense kind of that DGEM is what I'm trying to offload, and so I'm showing you how to do that. Okay, so on the host side, usually if you wanted to implement a full DGEM with NumPy, you would do something like this. You initialize some matrices. You actually convert them into a matrix data type so that NumPy understands when you do a multiplication between matrices, you don't want an element-wise operation, but a matrix multiply. And then DGEM is alpha times AB plus beta times C. Okay, so this is what I'm doing. Now, if you want to do that with offloading, all you need to do is import PyMike, right, the Python module. And then instead of doing this, you write down something like stream invoke the DGEM kernel on the device, passing in all the data that you need to do the DGEM. Okay? And what happens is, first, you get a handle to the target device that you want to talk to. PyMike uses a stream interface, so it's completely asynchronous. You can have multiple streams, or in future we will have multiple streams to target devices, so you can express asynchronity quite easily. And then you invoke whatever kernel you want. In this case, it's a DGEM kernel. You pass in the data that you want. And the key thing here is PyMike automatically understands what you want to do. Right? 1 second. So it automatically figures out that A, B, and C are matrices that you need to copy over to the device to run the kernel. So it will copy in, copy out those matrices. And for A, for M and K, alpha and beta, it would basically do copy in only. Okay, so it automatically figures it out. Yes, please.
Just going
I'll come to that in a minute. Yeah, next slide. And then at the end, I said it's completely asynchronous. So that means you just post an invocation request into a queue, and then you have to synchronize the host Python thread to wait for the final result. Okay? Now, the target site, and that's kind of a limiting factor of PyMag today. For performance reasons, you have to write C, C++, or Fortran code on the target. In a future version, I'm looking into at least supporting Python so that you can write some Python-esque native code. Okay? But basically, what happens is PyMag automatically does the unpacking and unmarshalling of data, and all you get into your kernel are nicely formatted pointers that you can just use. And in this case, I'm kind of a lazy guy, so I'm calling into MKL dgem in the BLAS interface to do the dgem. Okay? But you can also do something more complex and implement that yourself. All right? One word probably, so why this kind of sounds like an limitation. If you look at real Python HPC applications, there's a good share of number crunching code in low-level C or Fortran, so you can actually take that code and just modify it and move it over to the target device, right? Because that's your number crunching code anyways. Okay, so here is the automatic offload protocol from a very high level. So you got your host process, you got your target process, you got some offload data in a library, you load the library on the target device, then you do the stream invoke, passing in data as you see fit and what you need for the kernel, and then PyMag automatically figures out that it needs to copy in, for instance, A, B, and C in this case, and then at the end when the kernel is ready, we don't know if you changed it on the target device, so we do the copy out back to the host to transfer A, B, and C back again. Okay, for scalars, we skip the copy out because we know Python scalars are immutable, so you don't have to copy them back. Okay?
What about tubers?
No. We are so one of the assumptions is that you work on NumPy data, and you can't transfer Python objects or tuples or anything like that. Well, you can do that, but you need to somehow serialize them before you call into PyMag. Okay? Yeah.
So Matt's landing has the MCD RAM.
Right.
It's 16 gigabytes on there. And it's supposed to be 5 times more bandwidth than the standard OD RAM. So and then you can use it as a cache, or you can use it as part of the memory, or as a hybrid. So what is it doing? Do we need to worry about that at all?
So one thing I'm looking into with respect to Knights Landing support for PyMag is there are two options. Either you use Knights Landing as kind of a coprocessor node, then you are back to the regular offload model, right? The other thing I'm looking into is using kind of something I would call self-offload. So you run on the Knights Landing, you do an offload to the same Knights Landing processor, and then the copy in, copy out semantics basically would be take the stuff from DRAM and move it over to MCDRAM, run from the MCDRAM, and then put it back. That's the other usage model. Yes. Okay. So if you already noticed that copy in, copy out could be rather inefficient, right? So the C matrix, for instance, you don't necessarily need to move it over if beta is 0. Okay, you just need to transfer it back. At the same time, it's really superfluous that you copy A and B back, because usually if you do a real dgem, you don't modify them. Okay, now that's kind of the very high level view. You can go one step lower and now exercise control over data transfers. And this is what happens with PyMag. So you can modify this example to bind NumPy arrays to offload buffers. There's an interface for that. And then instead of adding your NumPy arrays to the invoke function, you just pass those offload buffers. And if you do that, PyMag basically recognizes the fact that you now explicitly want to exercise control over data transfers. And so here, data is transferred over to the device. Let me put in my animation here. So here now, it doesn't do any implicit data transfers anymore. And if you want to do a data transfer, there are functions update host, update device, so that you can control when a data transfer is enqueued into the system and in which direction this data transfer is happening. Okay, does it make sense? Okay, so this is now how it works. That's kind of the animation behind that. So again, you load the library, you transfer the code over, you do an update device to send the data over to the target, then you do the invoke, right? And then at the end, if you want, you can do an update host to transfer the data back. Okay? And now you got everything that you need to optimize and tell the system when a data transfer has to happen and which data transfer have to happen at all. Okay, let me show you an example. So one of my favorite examples is singular value decomposition, because you can actually nicely use this to do picture compression. So there's a nice looking handsome guy on the slide. So the upper left corner, that's the original picture. It's not blurred, it's actually me. And then the next to it, there's 99% compression. And how this works basically is you take the picture, you treat it as a 2D matrix, you apply the SVD decomposition, and what you get is a U matrix, a sigma matrix, and a V matrix, and then you throw away values from the sigma matrix. For instance, those that are close to 0, because they don't contribute a lot to the picture. Or you can just keep one single element of the sigma matrix, and that's what I actually did here. So this picture now is basically a scalar sigma, one element matrix, and you can already kind of see at least the dark white distribution of the picture. Right? If you increase sigma slightly, like going from one element to 2, you can also kind of recognize. Well, if you know that it's me, you can probably already start to recognize me. And this now down here is something like 20 elements in sigma, and basically you can't see a difference on the slides anymore. Right? So this is a very nice compression algorithm. It's highly efficient and it's easy to compute, right? Because it's just plus operations basically. Okay, so let's do that in Python. It's really easy. So what we do is, as I said, I'm lazy. So I'm using the NumPy package to do the SVD decomposition. And then reconstructing the image is really easy. You just do a couple of matrix multiplies to multiply U times sigma times V. And then you can reconstruct the image from the outcome from this DGEMM operations, basically. Okay. Now, if you want to do that with offloading, so what you need is a temporary array to hold the result of the first DGEMM application. You need a result array, and you need U, sigma, and V. Okay. Now, going through when the data has to be where, what you will see is that, the offload temp array, the temporary array, we don't have to have it on the host at all, right? We can just allocate some buffer space, some scratch space on the target device. And so what we do is we create an empty array on the target, and we tell PyMike that the host doesn't have to be updated at all. So this just creates some plain buffer space on the target device. Same for the offload result. So initially it is okay to have an empty array, and we don't have to have it on the host. So no data transfer needs to happen between host and target device. Then for U and sigma and V, we basically want to transfer it over, and this is what bind initially does. Right? If you bind a NumPy array to an offload buffer, the assumption is I want to send it over. Okay? I will show you in a minute how you can do that. And then basically it's 2 times DGEMM, so you run invoke kernel, you multiply U times sigma into offload temp, and then temp times V into offload result, and then you do offload result update host. Right? And all you get is 3 data transfers. 4. U, sigma, V, and the transfer back. Yes, please.
Do you know why the initial allocation of memory on the target takes so long?
Yes.
Can you tell?
Yeah, sure, I can do that. Of course. Is this a bad question? So no, the
Horrible, yeah.
you know, the problem there are two things that happen. First of all, allocation is a sequential process. Okay, so what happens is that you need to go into the operating system a couple of times to make available all those pages that you need. Okay, and then secondly, what happens is security. So what Linux does is when you get a newly allocated page, it has to null this page. It basically overwrites the page. And this is a sequential process. It's not that, you know, 250 threads are, you know, going through your allocation that you just did to write zeros into your allocated pages. That's one single thread doing that.
One slow thread on.
Exactly. Right? And since single thread performance on the KNC is much lower than on a Xeon, you're basically struck by that.
Actually, I see a solution how multiple threads can run in different areas on the.
Absolutely, you could fix it, but it's a lot of work.
Are they going to fix full engine?
No, likely no. But what you can do is so one of the tuning tricks that you can apply, but this is also true for PyMac. So let's talk about this. Is if you know that you need kind of the same type of scratch space all the time, you allocate it once, you pay the price for this allocation, and then you go through it and you offload to the same type of scratch buffer all over the place. So another project is actually sitting in here. Python is also using PyMic, and this is what Freddy, for instance, does basically. They allocate all of the space in the target and then do manual offloading into individual sections of this large scratch space that they allocated. Yes?
I'm not sure it's relevant to the talk, which is solved. Well, like in OpenMP, for example, there is a pool of threads which use transparently for user without starting a thread. Is it possible to lift the allocation mechanism above above the processor, right? And pre-allocate all the spaces for the whole program in the future and pretend to the user that they allocated them.
Okay, since this has nothing to do with Python, let's discuss it in the coffee break right after this session. Okay? Okay, no problem. I'm happy to answer those questions because that's my daily life basically. Okay, so yeah, I was here. So and then at the end you transfer the offload array back. You could reconstruct the image and you're done, right? And all you got is 4 data transfer, as I was mentioning. Okay, now for the interface that you have. So these are the generator functions. These are part of the stream interface to tell PyMic what data to associate with offload buffers. So this one you have seen already, that's the bind. So it basically takes an array and it associates an offload buffer with the original NumPy array. So anytime you do an update buffer, update device or update host, you will update the NumPy array. Okay, so the offload buffer kind of is associated with this NumPy array. There's also a copy function, which basically takes the NumPy array, copies it over to the target device, and then keeps the offload array separate from the original NumPy array if you need to retain the original version. And then there are functions like empty, where you can create an empty array of a particular shape. You can do an empty like. So if you already got a kind of a template array that you want to mimic, then you can do the empty like. There is zeros. So the array is allocated and filled with zeros. Zeros like ones. So if you need an array with all ones. And then there's a bcast function where you can broadcast a single value across the full array. If you know NumPy, this is exactly what NumPy offers you, right? So it's really meant to be on top of NumPy, basically. And then these are the operations that you have as part of the offload. So you've seen those guys here, so update device and update host. right? These are the ones that initiate the data transfers. Then you can fill an array with a particular value. You can fill from another array. You can zero out or one out the array. You can reverse it. You can reshape it, and you can flatten the structure into a flat array. And then we have, and this is why we have this additional library, there are additional operator functions. So you can actually express element-wise addition between two offload arrays. And what happens is that PyMac internally kicks off a kernel that does the addition on the target device. All right, so it's very convenient to program that from the host. And there are set slice, get slice, and all those accessor functions that you know from NumPy arrays. Okay, now performance. So this is a typical performance curve as you would see it when you do a micro benchmark of the bind operation. So that is including allocation and copy in and copy out. So the operations to just transfer data. And what you have said, you will see that the bind operation is gives you less performance, right? Because it has additional overhead of allocating the buffer on the target device, right? And there's also no surprise that if you transfer small messages, you're in the latency regime, so bandwidth is rather low. And then starting with something like a couple of 100 kilobytes, actually performance starts to go up so that you can see the full bandwidth that you would see from a PCI Express device. Yes, please.
So related to that, I heard that with large data sets, they push data through DMA channels.
Yep.
With small data sets, the CPU will push data.
Yep.
Where is that limit? Where this
I don't know. I'm not sure if we document it somewhere.
That makes sense because, for example, you with small data sets, it makes sense to aggregate data on the CPU side.
Yes.
And use DMA for faster.
Yeah, it's absolutely.
It would be good to know any advice on data sizes.
You can shoot me an email. I can try to find that out, but I don't have it top of my head, and I'm not sure if we ever published that, because that's kind of something that we would like to change from version to version to find better tuning spots or better.
For getting the best performance.
Yes, I know, absolutely. Okay, now for DGEMM performance, just a small micro benchmark here. So the light blue line, that's MKL. So MKL from a C program, C benchmark running on the host. And as you can see, you pretty much quickly achieve kind of the ideal performance, and it stays flat at about, 80%, 90% efficiency on the host system. The dark blue line, that's now NumPy with MKL. Right? So that is kind of what we are shipping today. And you can see that there's still, although we have those factors compared to the standard NumPy implementation, this is rather low. And the reason for this being so low is that if you want to codify a full DGEMM operation, you have to have alpha times A times B plus beta times C. So there's a lot of intermediate copies. If you would just use a standard matrix multiply without alpha and beta, then you would be close to that. Okay, but I just wanted to make a marketing case here, I guess. And then these are offload performance, so green or yellowish, that's the kernel performance, so that's what you see as gigaflop rate on the target device, and the orange line, that's the gigaflop rate, including all the data transfers, and naturally, since you're transferring data over, it's a little lower than the on-device gigaflop rate. Make sense? Good. Okay, now offloading in GPaw, right? That was just micro benchmarks. We want to see real application performance. So this is just a snippet of GPaw, one of the, 20 lines or so, maybe 10 lines out of 200,000 lines. So basically, there are NumPy-like generator functions to create the data structures. And so what we did is we basically intercepted, come on, go back. We intercepted those, and if we want to use a mic, right, we don't return a new array, but instead we bind the array. So basically, without changing a lot of code in GPaw, you can already, with a high-level interface, you can get pretty much far by just overloading those generator functions and where you create the data structures. You can intercept them, and then the data structures itself does the right thing, basically. Okay, so we ran that with a benchmark that simulates a lead atom on some C atoms. And so what you can see is the blue line here, that's host performance, so GPOR running on 10 to 40 nodes of the CSC system in Finland. And then the red curve here is the offload version, and lower is better because that's runtime. So time to solution, basically, from start of the benchmark to completion. And if you want a relative number, so over 10 to 40 nodes, we are able to sustain something like a factor of 2, maybe 1.6, let's make it 1.6x performance upside compared to the host-only execution. Okay. So, summary. So at least I was hopefully able to give you some insight into how you can use vTune to find hotspots and find out if they are offload targets. Certainly you can use them also for optimization targets. The other thing I wanted to tell you is the upcoming roadmap, right? So there's only so much I can do. So what I'm planning as the next features, and please let me know if they seem helpful to you. The first thing is I want to get away a bit from the native code on the target device by using Python, so that you can use some more Python-esque way of implementing the offload regions. Then PyMic right now misses events so that you can synchronize between the individual offload streams. And then, of course, you were asking that question basically. There is an upcoming next generation Intel Xeon Phi Coprocessor. So we actually want to support that in PyMic. Now the thing is, PyMic is open source. So I'm happy to have collaborators. If you're interested in implementing one of these features, please let me know. You can just pull the source, file a pull request, and I'm more than happy to incorporate changes into PyMic and make this a more community-driven effort. If you're interested in, so there's a GitHub page, github01org PyMic, where you can download the source code. The interface is rather stable now. It still didn't reach 1.0 state, so it's 0.6, I guess, is the current version. So things are still a bit in the flow, but it's stable enough to play with and to do some production runs on it. And if you're interested in more information, there's also a mailing list that you can subscribe to. It's really low traffic, so usually we are discussing a couple of issues that users have found, and I'm sending out announcements. So don't be you won't be spammed by subscribing to this mailing list. This is now the legal disclaimer. Usually I'm showing that at the beginning so that you know what you're after, and thanks for your attention. Thanks.